morning students into the 12th science chemistry class. We are learning the chapter number 2, that is the solutions. Into that we already learned the colligative properties and also the colligative properties for the non-electrolyte and electrolyte. What is the difference between them? We already learned. We learn about the Vant Hoff factor, how it is related to the colligative properties of electrolytes and non-electrolytes. That is, it is the ratio of colligative properties of the electrolytes divided by colligative properties of non-electrolytes. Again, the Vant Hoff factor I is also defined as in an alternative manner. The Vant Hoff factor, that is the I, is also defined in alternative manner, and exactly that is the equivalent manner as I is equal to actual moles of particles in solution after dissociation of that of the electrolytes. We are learning here this is the about the electrolytes. So I is equal to actual moles of particles in solution after dissociation divided by moles of formula units dissolved in solution. For example, now this is for both non-electrolyte and electrolyte, and we know that the non-electrolyte does not dissociate into the water. So actual moles of particle in solution after dissociation remains same as that of the moles of the non-electrolyte which we dissolved into the solution. The number of moles of the non-electrolyte, that means the number of moles of non-electrolyte after dissociation and before dissociation are same. So in case of non-electrolyte, this Vant Hoff factor I is always 1 because same divided by same number of moles, that is equal to 1. But for electrolytes, the value of this Vant Hoff factor I may be different, because some electrolytes are, that is they are having 2 or 3 or sometimes 4 ions also after dissociation. They ionize into 2 ions or 3 ions or 4 ions and again so on. And therefore the value of I changes for the electrolytes. Now see here, thus I, that is the Vant Hoff factor, is always 1 for non-electrolyte as they are not dissociated. That means after dissociation and before dissociation the number of ions remains number of particles remains the same for the non-electrolyte. So their Vant Hoff factor I is always 1. But for electrolytes such as KNO3, now how the KNO3 dissociate into the water? As K plus and NO3 minus, that means 2 ions are there. So here I is equal to actual moles of particles in the solution after dissociation becomes 2, and moles of formula unit. Now suppose this is the 1 mole. For 1 mole 2 ions after dissociation and the formula unit is the 1. So 2 divided by 1, that is becomes 2. So the value of I for this KNO3 is 2. Also for NaCl, it dissociates as Na plus Cl minus. So I is equal to here also 2 ions if there is the 1 formula unit. So 2 divided by 1, that is equal to 2. So actual moles of particle in solution after dissociation divided by moles of formula unit dissolved in solution. Now this is the that is I can be calculated by using this formula. So here I is equal to 2 divided by 1, that is equal to 2 for both this KNO3 and NaCl. Now similarly for Na2SO4, that is the sodium sulfate. This is the potassium nitrate and sodium chloride. For that potassium nitrate and sodium chloride, the value of Vant Hoff factor is 2. But for sodium sulfate, it ionizes as twice Na plus because there are the 2 Na ions ions, sodium ions. So twice Na plus SO4 minus. Now two negative charges on that of the sulfate ion. So as this Na2SO4 ionizes in this way, so there are totally 2 plus 1, that is the 3 ions or particles after dissociation. But the formula unit is here 1. So the value of I, that is the Vant Hoff factor, becomes 3 divided by 1 is equal to 3. Similarly, for calcium chloride also, it ionizes as Ca2 plus twice Cl minus. That means there are 2 plus 1, that is the 3 ions, and so for both of these, sodium sulfate and calcium chloride, I is equal to 3 divided by 1 is equal to 3, and so on. Thus students, in this way the value of I changes for the electrolytes as they ionize in how many ions. Thus the colligative properties of these electrolytes are twice or thrice respectively. Twice and thrice respectively, because to that of non-electrolyte of the same concentration. While the colligative properties of these electrolytes are twice or thrice of that of the those of the non-electrolytes, because they ionizes in 2 and 3 ions, and therefore the value of I changes. And thus the colligative properties of these electrolytes are twice and thrice respectively as those of non-electrolyte of the same concentration. Remember that. Of the same concentration of non-electrolyte, the electrolytes colligative properties are twice and thrice respectively. Now consider the modification of expressions of colligative properties of non-electrolyte for applicable for electrolyte. Now how the expressions are applicable for electrolytes, and these expressions of non-electrolyte must be modified for the application of the that is the colligative properties of electrolyte. So modification of expressions of colligative properties of non-electrolyte for applicable for the electrolytes. Now how the 4 colligative property changes their formula or expression changes, let us learn. Now we know that the colligative property, that is the lowering of vapor pressure, delta P is equal to P01H2 and that is equal to W2M1 divided by M2W1. We learned this already. But here as we have to applicable this or apply this for the electrolyte, so just multiply these colligative properties by the Vant Hoff factor I, and therefore it becomes delta P is equal to I P01H2, that is equal to I W2M1 divided by M2W1. Now in this way by multiplication with the Vant Hoff factor to this colligative property, we obtain the expression for the colligative properties of the electrolytes. The second colligative property, that is the elevation in boiling point for non-electrolyte, is have the expression delta TB, that is equal to Kb into M. M is the molarity, and it is equal to, that is the 1000 Kb W2 divided by M2W1. Now only just by multiplying these colligative properties of non-electrolyte by the Vant Hoff factor I, we obtain the colligative property for the electrolytes, that is the elevation in boiling point as I into Kb into M, that is molarity, Kb is the molar elevation constant, that is equal to I into 1000 Kb W2 divided by M2W1. And we know that here this W2 is the weight of the solid, W1 is the weight of the solvent, and M2 is the molar mass of the solid, Kb is the elevation, that is molar elevation constant or ebuloscopic constant, and I is the Vant Hoff gap. Similarly for the depression in freezing point, this is the third colligative property. For non-electrolyte, delta TF is equal to Kf into M, but for electrolyte W1. Now in this way, this colligative property for electrolyte only changes by multiplication of the Vant Hoff factor. Now this pi, that is the osmotic pressure, is equal to for the non-electrolyte it is mRT. M is the molarity here, remember that. And by multiplying with the Vant Hoff factor, this pi is equal to ImRT. R is the gas constant, T is the temperature, and capital M is the molarity. In case of osmotic pressure, we use the molarity because osmotic pressure is temperature independent or at constant temperature. Now, osmotic pressure is equal to W2RT divided by M2V. Now here W2 is the weight of the solid, R is the gas constant, T is the temperature, absolute temperature or temperature in Kelvin, M2 is the molar mass of the solid, and V is the volume of the solution. And in this way, by multiplying with just the Vant Hoff factor to the colligative properties of the non-electrolyte, we obtain the colligative properties expression for the electrolytes. Now let us learn the next topic. There is the numericals are possible on this topic. Let us learn now. Now students, you can take the screenshot for writing the notes. And you write all the notes in your notebook in a beautiful handwriting. Now pay attention students on the blackboard. Now Vant Hoff factor and degree of dissociation. Now for weak electrolyte, we must involve the concept of degree of dissociation, that is the alpha, because weak electrolytes are very rarely ionized. They are not ionized very much, and so we must involve the factor, that is the degree of dissociation. In 11th standard, we know that alpha is the degree of dissociation for the weak electrolyte, as weak electrolyte dissociate in a very less quantity. And so for the Vant Hoff factor for the weak electrolyte, we must involve this concept of degree of dissociation alpha. Now that changes the degree of dissociation, changes the Vant Hoff factor value, that is the I. Now consider a weak electrolyte AXBY. Now it dissociates as AXBY is equal to XAY plus YBX minus. Now we know that how it is possible. Suppose this AXBY, suppose it is the this HCl, suppose, or it may be PB or AgCl also, that is the weak electrolyte, and also that is the ammonium chloride is also weak electrolyte, but there are one cation and anion, and so let us consider the PbNO3 twice. Now suppose this is the weak electrolyte. Now how it is ionized? It ionizes as Pb2 plus twice NO3 minus. Now as here only one cation but having the 2 plus charge. Now this 2 comes from Remember that. Similarly here, Y anions but having the charge X minus. As here only minus charge, one minus charge because lead cations are only one. So here is the only one minus charge. Now in this way, from this example, you can understand this. Why I write here the dissociation of AXPY as XY plus YB. Sorry, XAY plus YB X minus. Now initially when we take this, that is the weak electrolyte AXBY, it have only one mole. And initially there is no dissociation. When there is no dissociation, so number of cations and anions are 0 mole, 0 mole. But at equilibrium, when this AXBY get dissociated at equilibrium, as it is the weak electrolyte, it is not completely dissociated. So only alpha moles of it dissociate. Suppose alpha is the degree of dissociation. So at equilibrium, what is the remaining moles of the AXBY? Now initially it is 1 mole and only alpha mole get dissociated because it is the weak electrolyte. It is not completely dissociated as 1 mole totally. So only alpha moles get dissociated. So after dissociation at equilibrium, the remaining number of moles of this AXBY is 1 minus alpha mole. Because only alpha get dissociated, so subtract the alpha from 1 to obtain the remaining number of moles of AXBY after dissociation at equilibrium. And at equilibrium, the number of moles of cations and anions will be X alpha and Y alpha. Because if alpha get dissociated or if one completely get dissociated, then 1 mole of A plus and 1 mole of B. But as there are only alpha get dissociated, but the X moles of A and Y moles of B are there, so this becomes X alpha and Y alpha moles. Remember that. Now, if alpha is the degree of dissociation of weak electrolyte and X alpha moles cations and Y alpha moles anions are present at equilibrium, then what is there at equilibrium? There are the X alpha moles of cations and Y alpha moles of anions are present. Then what happens? We have dissolved just only 1 mole of electrolyte initially and alpha mole of electrolyte dissociated. So 1 minus alpha mole remains undissociated at equilibrium. As I tell you here, at equilibrium only 1 minus alpha moles remains undissociated. And the total number of moles, that is the at equilibrium, how we can calculate then? This total number of moles at equilibrium is 1 minus alpha plus X alpha plus Y alpha. So the total of moles after dissociation at equilibrium is 1 minus alpha plus X alpha plus Y alpha. Now solve this as 1 minus alpha plus X alpha plus Y alpha. Now here alpha is, in this, alpha is common. So this 1 as it is and take the common alpha. Now here is the plus sign. Now this is the common, that is the alpha. Then what is here remaining? Minus 1 because we take here plus. So in bracket, as this alpha is out of bracket, here only 1 is remaining but this minus sign is there. So minus 1 plus X plus Y because alpha is common. Now adjust this as X plus Y minus 1. So it becomes 1 plus alpha X plus Y minus 1. But here X plus Y are the number of, that is the moles of the ions, that is N. Suppose X plus Y is equal to N. So X plus Y substituted as the N, which are the total moles of ions. So put the X plus Y as N here. So it becomes 1 plus alpha in bracket X plus Y as the N and this minus 1. Now these are the total number of moles after dissociation. Now we already learned just now the formula of the Vant Hoff factor, or define alternatively the Vant Hoff factor as I is equal to actual moles of particle after dissociation divided by moles of formula unit. Now actual number of particle after dissociation are 1 plus alpha n minus 1. So substitute here I is equal to 1 plus alpha n minus 1, and the formula, that is the formula unit for that is the ax plus by, that is only 1 is there, so divided by 1, and it becomes only 1 plus alpha n minus 1. So I is equal to 1 plus alpha n minus 1. Now this 1 is taken here, so it becomes I minus 1 is equal to alpha n minus 1. But if we want to calculate alpha, then what becomes? This alpha becomes as I minus 1 divided by n minus 1. Can you understand, student? How it becomes? Alpha is equal to, if we want to calculate this alpha, just subtract this one from this I. So I minus 1, and this get divided, as here it get multiplied, so it get divided by going to the left hand side. So alpha is equal to I minus 1 divided by n minus 1. Now this is the relation between the degree of dissociation and Vant Hoff factor for the weak electrolyte, that is alpha is equal to I minus 1 divided by n minus 1, where I is the Vant Hoff factor, alpha is the degree of dissociation, n's are the moles of the ions. Now students, this is about the that is the relation between the Vant Hoff factor and this degree of dissociation of weak electrolyte. So student, if you understand all these expression, that is the degree of dissociation and Vant Hoff factor relation, how it is obtained as the alpha is equal to I minus 1 divided by n minus 1, and also you understand about the expressions for the electrolytes from that of the non-electrolyte for all the 4 colligative properties, and also we learn about that is the how we can calculate the I, that is the Vant Hoff factor for the electrolytes and non-electrolyte. Then you can share, subscribe and like this video, and also you must tell to the other students, that is another student of the another different colleges, so that they also get benefited by watching this video, because this is the very interesting topic and which is very important into the examination point of view. So students, thank you for watching this video. We will solve some numerical based on this Vant Hoff factor tomorrow. Now you will be always welcome into this 12 science chemistry class into the next lecture also. Thank you for watching this video. Now students, you can take the screenshot of this blackboard writing, so as you can easily understand this topic. This is very important topic for the examination point of view. So best of luck for your study. All the best. Stay fit and stay, that is the intelligent.